Hello everyone, welcome to the live interaction session of week 5. We'll start in a couple of minutes. Okay, so let's start. Um, so um, I was asked to cover spectral indices also from the last week. So we'll start with spectral indices, then we'll look into some concepts of photogrammetry, we'll solve some problems, and then we'll look at thermal infrared remote sensing. So, yeah, spectral indices, they're the combinations of pixel values from two or more bands in a multispectral image. So these spectral indices, they are used to highlight the pixels which contain or lack a specific type of land cover which is of interest to the user. So these land cover types can be uh, yeah. So we have various land cover types like vegetation or water, snow, soil, built up index, built up area, and so on. So there can be more such vegetation cover types which we want to highlight. Uh, yeah, from the uh, single band images. So we use different combination of these spectral bands to in order to highlight these specific land cover types. So there are different indices like for vegetation we have NDVI, for water there is uh, NDWI, for snow we had NDSI, for soil it was HDSI, NDBI. So, and there can be multiple such indices for each land cover. So, these indices have been updated through time to give better and better um separation from their surroundings. So, most of the indices they are normalized difference. So, there would be this normalized difference would be a difference between two spectral bands which highlight the characteristics of these particular types of land covers. So we'll look at some of these indices and try to understand they um, how they help us enhance these features better. So first is normalized difference vegetation index or NDVI as we know it. So NDVI, there has been the need to monitor vegetation consistently through time, and that includes various purposes like monitoring agriculture or monitoring the forest cover, or there could be wetlands or manicured urban vegetation and so on. So for that, uh, this index has been generated, which uses the spectral characteristics of vegetation. So we'll look at it through the spectral reflectance curve first, and then we'll try to understand. So yeah, so this is the this green curve shows the spectral reflectance feature of vegetation. So here, uh, this is the visible range, and we see that there are two absorption bands here and here, and then after that we have the near infrared range where the vegetation reflects very I mean it shows very high reflectance. So this index is used to monitor the health, the vegetation health. So we'll look how it does that. So the NDVA is calculated as NIR minus red divided by NIR plus red. Yeah. So the characteristic feature of vegetation is that it reflects very high in the NIR region and it absorbs in the red region. So we calculate NDVI by normalizing the difference between NDVI and red. So higher the difference between these two reflectances, more would be the vegetation cover. I mean, that would define the presence of vegetation in that band, in the NDVI band. So, if this is my band 4 and band 5 in Landsat, so when we calculate NDVA, this calculation will happen on each pixel of these two images. So for this pixel 1, we'll have band 5 minus band 4 divided by band 5 plus band 4 in pixel 1. Then for pixel 2, we'll have the same operation. So that is how we will obtain this index. Yeah, so one of the benefits of taking this difference is there might be other features which are showing similar reflection characteristics in one of the regions. So if we use only band covering that spectral regions, we might not be able to differentiate between those two. But then when we take difference between two different bands, it enhances the the feature that we want to highlight. So here, suppose there is soil also, which reflects more in the near infrared region. But if we were to take difference between near infrared and red, so for soil, the difference between near infrared and red would be very less, but for vegetation, it would be high. So that would enhance it from the background soil. Yeah, and coming to the left region, so more so healthier the vegetation, the more it would reflect in the near infrared, and more it would absorb in the red region. So the difference would be more. So we will have higher NDVI values for a healthy vegetation, and if the vegetation is unhealthy, then it would reflect low in near infrared and absorb less in red. So the difference would be less and NDVI would be smaller in this case. So monitoring NDVI over a region for a certain amount of time we can see if the vegetation health is changing or it's getting affected through time in an area. We can also monitor if the vegetation cover is increasing or decreasing in an area. So there are many such applications for using this index.
Could you please repeat, if vegetation is healthy, then what happens?
Okay, so if vegetation is healthy, it will reflect more in the near infrared region, and it will absorb more in the red region. So for a healthy vegetation, you will have a depression over here and there would be a high peak. And for an unhealthy vegetation, this absorption would be less. So it would be less than this, and reflection in the near infrared would also be less, like this. So if we were to take a difference between these two, then for this unhealthy vegetation, this value would be lesser than this healthy vegetation. Is that clear?
Yes, means NIR minus red is higher for healthy vegetation, right?
Yes. Yes.
Okay. Thank you.
Okay. So this figure is shows an example of how we can use NDVI index to track changes in the vegetation cover. So on the top left, this image, it's from year 2000. It's a true color image from Landsat 7. So this image, it shows a river, and then there is some vegetation cover surrounding it. And here on the bottom figure, we see the NDVI image for the same scene. So here in NDVI, we can see that the vegetation feature, it has been enhanced as compared to the true color image. And we can also clearly see the uh, water body and other surrounding pixels. And on the right, there is second image, which is from year 2015. It's from Landsat 8 and it's a true color image. So on the bottom, we see the NDVI image corresponding to that. And from these two images, we can see that the vegetation cover has drastically reduced in these 15 years. And then most of the green patch which we could see on the left hand side, it has turned yellow or reddish. So these indices would correspond to different land covers, and so the vegetation land cover has been replaced by these land covers. So it could be barren soil or something else. So this is one of the applications of NDVI to keep track of changes in the vegetation cover. Okay, then another index is NDWI. So this index is used to highlight pixels with water bodies or moisture. So if we look at the spectral reflectance curve of water, so we have seen this figure before. So this curve shows the spectral reflectance properties of water. So when we were looking for vegetation, what we did is we picked 2 points where um, the vegetation was reflecting the highest and then it was reflecting the lowest. So the point of highest reflection and highest absorption, we took those points. So here in case of water, if we want to enhance the water feature, then we would have to take the difference between the point where water reflects the highest and where it absorbs the highest. So we know that in green band the water reflects the highest. So we would take this point, and then from infrared onwards, water is showing absorption feature only. I mean, water does not reflect from point 0.7, point 0.72 or something onwards. So we can take any region from that area, and we have to take the difference between that region and green to enhance the water feature. So NDWI. So this is one of the formulas of NDWI. So there are other formulas which have their own logics. So these formulas keep updating with time. So this is the formula that I found. So this is green minus. So green minus short wave infrared. So it would be this difference. So now so, photogrammetry is the science of obtaining reliable information about properties of an object or surface using the remote sensing information. So, we had seen some of the concepts from photogrammetry in one of the earlier sessions, but we'll try to cover it in more detail in this session. So, there can be two types of photogrammetry. First is aerial or space-borne photogrammetry, and second is close-range photogrammetry. So, in aerial photogrammetry, it consists of any photograph taken from an airborne vehicle. Whereas in close-range photogrammetry, the images are acquired through handheld instruments. Yeah, so aerial or spaceborne photogrammetry, it is mainly used to study the surface features of Earth or other planets. Close range photogrammetry, it can be used to look at objects from the ground. So we can look at any objects or feature. And this close range photogrammetry is mainly used in industrial purposes. So these two images show examples of aerial and close range photogrammetry. So first we'll look at aerial photogrammetry. So uh, yeah, so there are two types of aerial photographs. First is a vertical photograph, and then there is tilted photograph. And tilted photographs are classified again into low oblique and high oblique. So let's look at how a vertical aerial photograph would look. So so this is the camera over here. So in vertical aerial photograph, the camera is pointed as straight down as possible. So uh, the optic axis of the camera is parallel to the plumb line. So the line joining nadir point and the camera is called plumb line. And this is the point which is vertically below the camera. It is called nadir. So the image captured over here, it would be formed on this film, and f here is the focal length of the camera. So in this case, this lens axis is perpendicular to Earth's surface. So this image, the vertical aerial photograph, it covers relatively smaller area. And the shape of the ground covered, it would be square or rectangular, and the shape of the image captured would also be same. And in this case, the directions and relation between 2 points on the ground, so distances between 2 points on the ground would be preserved. So the scale of the image would be same everywhere. uh, Yeah. Also, in a vertical aerial photograph, the relief might not be so apparent. So, if there is this tall building right below the camera lens, we might not be able to perceive the height of that building if the camera lens is directly on top of it. Uh, Second, we have tilted photographs, in which first we'll look at low oblique. So for low oblique, so this is the optic axis of the camera. So for low oblique, uh, the optic axis would be around at an angle of 30 degree from the plumb line. So this would be around 30 degree or within 30 degrees. And here, so the major difference from the vertical aerial photograph would be that here the area which is captured by this photograph, it would be trapezoidal, but the figure acquired would be square or rectangular. Also, in this case, the scale would not be same everywhere. So there might be some distortions in this image due to the tilt of the camera. So the objects closer to the camera might appear bigger and the farther objects might appear smaller. So the scale of the photograph would not be same throughout. But in this photograph, we cannot see the horizon, so the horizon wouldn't be visible. Here, the relief would be more apparent than that of the vertical aerial photograph, but again, it would be distorted. And then second, we have high oblique. So here in high oblique, this angle would be up to 60 degrees. And the major difference from low oblique would be that in this figure, the horizon would be visible. Also, the high oblique photograph, it would cover a larger area. So this is the classification of aerial photographs. Yeah, now we'll look at the overlapping stereo photography.
Will you please show previous one, previous slide? Okay.
Yeah. So sometimes to cover a specific area, I mean to map the entire area, we might need to uh, we might need to overlap the images to cover the entire area. So and this overlap, it is also important to join different images together. So we can look at the common points between different images, and then these images can be placed together in a proper manner. So this first image, it shows an example of longitudinal overlap. So this is the direction of light, and here we see that each two adjacent images, they are showing 60% overlap. So, and this is the total coverage of the photograph. So every two images, they will have 60% of the portion which is similar. And here, um, so uh, after covering the first line, the aircraft takes a turn and goes back. It takes a turn, goes back again. So along with the longitudinal overlap, the images also have a side overlap. So this is flight line 1, this is flight line 2, this is flight line 3. So here we see that these images have sidewise also, they have some overlap, and here also longitudinally they have some overlap. Now let's look at the scale concept in vertical aerial photograph. So the scale is the
Will you please go to previous slide? So there is a concept side lap and end lap. So here side lap, it is written it is 20 to 30% of side lap. And regarding end lap,
sorry.
End lap. End lap. In the lecture video, there are two concepts. One is end lap, other is side lap.
Okay, I think
Side lap.
calling a longitudinal overlap, that would be the end lap. So the images, they have two kinds of overlap. So first you have along the flight direction, and then after the flight takes a turn, it would start scanning in this line. But then here, the image would not start from here directly. There would be a small overlap on the side as well. So that would be the side overlap. And here you have, I think this would be the end overlap.
That's 60% overlap, whatever written. That is the end lap, we can think.
Yeah, right. So this is along the flight direction.
Okay, thank you.
Right. So scale is the relationship between distances measured on the photograph and the actual distances on the ground. And scale is a reduction factor by which the real world is represented in the photograph. So there are different such definitions of scale. We have certain indices to which help us get an idea about the scale. So let's look at each of these indices. So representative fraction, or RF, it is the ratio of photo distance by ground distance. Or it is also it can also be defined as the ratio of focal length of the camera divided by flying height above the terrain. So these two ratios can give us the representative fraction. Then we have photo scale reciprocal, which is the reciprocal of RF. So it's 1 by RF. It's equal to ground distance by photo distance. And the reciprocal of this also. Equivalence map is the ratio of distance on the photograph to the same distance on ground, but expressed in a different unit. So when we are expressing equivalence map, we can express it as like 1 centimeter is equal to 1 kilometer or something. So it would be like 1 centimeter on the photograph is equal to 1 kilometer in the ground distance. So we'll try to do some numerical problems based on the side lap overlap concept and scale. So maybe you can try this problem for a while. So here I have drawn these photographs according to the percentage of overlap that was given. So the longitudinal or end lap, this is 60% and the side overlap is 30%. So here let's label the photograph. So this is 1, 2, 3 and so on. So here, this is the this part is the overlap between these two adjacent photographs, and this is the side overlap. So the effective area which is covered by this photograph would be, so if L is the total length of this photograph, then if it has 60% overlap, then the effective area that that particular photograph is covering would be L into 1 minus 60%. So it would only cover 0.4 times L of area. So that would be the effective length which is covered on that side, and here in the vertical side it would cover L into 1 minus 0.3, so it would cover 0.7. So L, if this is B, 0.7 times B, and so on. So we calculate the effective area which one photograph is occupying, and then we calculate total. We know total area, and then we divide the area of one effective photograph. We divide the total area by area of one effective photograph, and then that is how we will be able to calculate the minimum number of photos required. So in this image, we have one photograph with dimensions 20 centimeter cross 20 centimeter. So first, this L is 20 centimeter, and there is 60% overlap on the side. So we have 20 into zero point 0.4, which is 8 centimeter on the side, and in the longitudinal direction, and vertically we have 20 into, so this is the other dimension, so we have 20 into 1 minus 0.3, so it would be 14 centimeters. So this is the effective area of each photograph, right? Now we will convert this to a to the ground distance of each photograph. So it is 8 centimeter into 14 centimeter is the area of each photograph, right? And when we convert it to ground distance, so for conversion to ground distance, we have 1 centimeter is equal to 100 meters. So 1 centimeter on the photograph is equal to 100 meter on the ground. So I need to multiply 100 to both the dimensions. So 8 centimeter I'll multiply by 100, and 14 centimeter also I'll multiply by 100 to get the ground distance. So my ground distance would be into 10 to the power 4. So this would be meter square, because I converted from centimeter to meter. Now N is my total area is 150 square kilometer. So I need to convert the scale to SI units. So 150 into 10 to the power 6 meter square divided by 112 into 10 to the power 4. So it would be 133.92, which will be approximated to 134. So the minimum number of required photographs would be 134 in this case. Is this clear? Okay, let's move on to the next problem.
Please show last slide. Yes, it is done.
Okay, so maybe you can try this problem for a while. So let's try to. Did anyone get any answer? Okay, let's try to solve this. So this is the point which which is at the ground level, and the elevation of that point is 1400 meters above the mean sea level. And they have given the scale of the photograph as 1 is to 7500, and focal length is also given. So we saw in representative factor that scale can also be given as f by so focal length by distance between the uh, camera and the terrain, or height above the terrain, distance between camera lens and terrain. So if I call this as small h and this as capital H, then my scale would be given as f. So this is f focal length, f by capital H minus small h. So this is the distance OB, which is the distance between camera lens and the terrain. So we need to find that distance in order to be able to find flight altitude above the sea level. So here we have a scale as 1 is to 7500, focal length is 15 centimeter. So h minus h would be or 1125 meter. So this much distance is 1125 meter, and this is 1400 meter. So total height of the aircraft above the sea level, it would be 1125 plus 1400. Sorry, the scale is not correct. So this would be 2525 meters. I hope this is clear. You can try to solve this problem if the last one is clear. So in this problem, there is a photograph also and a map, and the scale of the two would be different. Alright. So this is A, this is B. These are the two different points on the photograph. So it's given that the distance between these two lines is 10.16 centimeter, and the focal length of this photograph is 16 centimeter. This same line on a map, it has the length of 2.54 centimeter, and the scale of this map is given, which is 1 is to 50,000. So this entire terrain, uh, it has an average elevation of 200 meters above the mean sea level. Right. So we need to calculate the height of the aircraft, flying altitude of the aircraft above mean sea level. So here, what we'll do is, they have given us the scale for this map. So we will calculate the true ground distance from the map to. So from the map, we'll calculate the true ground distance between points A and B. Then we'll use it to find the scale in of the photograph, and from that we'll use it to find the altitude above the mean sea level. So from here we know that scale is photo distance by ground distance. So, so this is the actual ground distance. Now in this figure we can calculate the scale, which is photo distance by ground distance. So the distance between A and B, the ground distance would be the same here. So we have 10.16 divided by 127,000. So this ratio is 1 to 500. And we also know that scale is equal to focal length divided by height above the terrain. So this is h minus h. Right, now we know the focal length also. So height above the terrain would be 216. So this is 2000 meters. So we know that. So this height is 2000 meters. So the flying altitude of the aircraft would be 2000 plus 200 above the sea level. So it would be 2200 meters. This is clear, I hope.
A, a quick clarification. See, when they're asking for to find the flying altitude, right? It's on the ground level. I mean, like ground reality. They're asking.
Yeah, here in the question it's given calculate the flying altitude of the aircraft above mean sea level.
I mean, that is the the real height of
Yeah,
altitude of the flight. right? And the given points are AB, line AB appears to be 10.16 centimeters on a photograph, which is related to the photograph scale,
Hmm.
and focal length is also okay. Okay, the corresponding measure is 2.4 on the map. So, what is exactly the map mean in like map and photograph?
Okay, okay. There are topographic maps which are generated using geological surveys and all. So they are not exactly captured from the satellites, but they are actually prepared using field measurements.
Okay.
Huh. So that is the map and a photograph.
Okay, that means map also is it's a ground reality. What we can say, in situ scale.
No, it wouldn't be in situ scale. So the map would be drawn on a paper itself, right? So it would
Okay.
be a small scale representation of the ground data. So the maps have become outdated now because of the satellite images. So um, in some areas we can use, if the maps are available, then maps and photographs can be used together to obtain such information.
So the when this 2 centimeters is corresponding to the scale with the 1 is to 50,000 ratio.
Huh.
Okay.
So here we don't have the data of actual ground distance between A and B, but then still if we have the map, we can find the actual ground distance.
Okay.
Slides of the uh, so are you getting the height 1270? So this 1270 meters is actually the ground distance between point A and B. So this point between point A and B, this distance is 1270 meters on the ground. So it is not the vertical distance, right? Yeah. Okay. Okay. So let's look at the concept of stereoscopic parallax. So this stereoscopic parallax is the displacement of an object caused by change in the point of observation. So that is called parallax, and stereoscopic parallax it's caused by taking photographs of the same object from different points of observation. So look at this figure on the right bottom. So here, when the photograph is taken from location L1 and when it's taken from the location L2. So here, this is my optic axis. No, this is the nadir point, and here A and B have these positions. And when the photograph is taken from another position, we see that B and A, their positions they have shifted with respect to this O point. So because their positions have shifted, it will appear differently on the photograph. So if we look at this photograph on the left, these are the two pictures which are taken from uh, different stations. And here we see that this is the top, and this is the position of the top of that structure in two images. And then we see that in the image on the right, the bottom part of the structure is not visible, but then here on the left we see that the position of the bottom part of the structure is there. So this difference of the distance between this top and bottom, it would be called the differential parallax. And then this concept of stereoscopic parallax, it can also be used to find the height of these objects. So where h prime is the, so this is the formula to find the object height using stereoscopic parallax. So here h is the object height, but we need the information about the flying height beforehand itself. We need the information about differential parallax, which is this, and then we need the average photo base length. So this average photo base length, it's the difference between the principal point and conjugate principal point. So that part was covered in the lectures. I hope this is clear. Okay, so we'll start with thermal remote sensing now.
So in the previous one, you just go to previous slides. Differential parallax. Will you tell again?
Okay.
Differential.
Yeah. So this is x1. It's the line joining the top of the same structure in the two images. So this is that much distance, and then there is x2, which I have drawn here. This. So it is joining the bottom part of the two structures. So in the right image, the position of the bottom part of that structure is same as the top part, but then in the left image, that position has shifted. So when we calculate the difference between these two lengths, it will give us the differential parallax. So this is x2 minus x1. This is the difference between these two. Is it okay?
Okay.
Okay, so we'll start with thermal remote sensing. So we know that any object above 0 degree Kelvin emits electromagnetic radiation. So when we are looking at remotely sensed photo image, then suppose you are looking at a landscape, then all the features in that landscape would also be emitting some energy in the thermal infrared region. So this energy is emitted in this 3 to 14 micrometer range, which is the thermal infrared region. So, but our eyes are only sensitive to the short wave visible range, which is 0.4 to 0.7 micrometer. Right. So we can only see the range from 0.4 to 0.7 micrometer, and beyond or like above or below that, our eyes cannot sense those. So these micro thermal infrared radiations, which are in this range, these would not be sensed by our eyes, right? So multiple sensors have been devised which are sensitive to these small changes in thermal infrared radiation, so that we can use our remotely sensed instruments, and then we can find and look at these subtle changes in the thermal signatures of various objects on Earth's surface, and then we can see how it helps us understand their thermal properties better. So yeah, so look at these images as an example. So here, this is the first image. This is the thermal infrared image of this F-116 jet in flight. and then we see that these portions of this jet, they appear they are appearing brighter than the rest of the image. So we can interpret that uh, these uh, these portions of this jet engine, they are emitting higher than as compared to the rest of the parts of this jet. Okay, in the next image, what we see that this is the thermal infrared image of radiant energy from a residential house. So through the windows, we see that the windows appear brighter, and then the roof and rest of the parts, they appear slightly darker. So it means that higher energy is being emitted through these windows. Similarly, we can see for the windows of this third image, or here we can spot these people in the darkness. Here, this is the engine of this helicopter, or here we see that there is a jet which is appearing brighter, or this image in G, this is the thermal image of power transformer revealing very hot wires, and so on. So this is a boat, and we can spot all the people around surrounding. So thermal imaging technology, it can be used to obtain knowledge about the surroundings uh, in a different way. So we can sense the temperature that these bodies are emitting, and then we can obtain different information about our surroundings. So it has applications in medical field also, in military also. It has several applications. So we'll try and see the basic principles of this thermal infrared remote sensing, and then we'll look at some physical laws which are there, and then we'll try to solve some numericals. Okay, so we just saw that all the objects above 0 Kelvin, they will be having some sort of kinetic energy within them. So,
So, excuse me, as you told, our eye can see only a particular range, isn't it? So, whether it will come under active remote sensing or passive remote sensing?
our eyes,
Yes.
it would be, I mean, see, if we are looking at um, objects surrounding us with sunlight, then it would be so if the sunlight is reflecting, then it would be passive remote sensing. Yeah, but no, it would be passive remote sensing in any cases, because we don't have a source of light inside our eyes, right? So it would be passive remote sensing. Even if we are using tube light, it would be another source, and then we would be looking at it. So it would be passive remote sensing only.
Okay. Thank you.
Yeah. So suppose these are the particles at certain temperature T1. So these particles, when this T1 is greater than 0, these particles would be having some sort of energy, right? So the energy which is there because of the kinetic motion, it would be stored as kinetic heat. So this is the energy of the particles in random motion. And kinetic temperature, so this kinetic temperature would be the measure of the concentration of heat of these particles. So concentration of heat. So we have T kin. So this is the kinetic temperature, which is the actual temperature of that body. So if we want to measure the kinetic temperature, then our measuring device should be in contact with the body. So it would be like measuring with a thermometer or something. So this would be in situ measurement. So when we touch the body and take the temperature, then that would be the kinetic temperature of that body. But in remote sensing, whichever temperature that we are sensing, we are looking at it from far apart. So when these particles are in kinetic motion, they collide with each other, and then they also radiate some electromagnetic radiation. Now this radiation is called the radiant flux. So yeah, so this is radiant flux, which is the uh, amount of energy being emitted by that body. And then radiant temperature, this is the concentration of amount of radiant flux exiting an object. So this is T rad. So it has been observed that there is a very direct correlation between T kin and T rad. Right. So there is a correlation which is established between the kinematic and the radiant temperature. So this plot on the right side, it shows the linear regression of remote sensing derived water temperature, which is T rad, versus the true kinetic water temperature, which is T kin. So T rad was measured using the satellites, and T kin it was measured using the thermometer. Obtained by in situ measurement for 4-year service in 5 different streams. Okay, so here we see that R square is almost around 0.99. So we see that there is a good correlation between the radiant temperature and kinetic temperature. So we can use this property to. So this is the main principle of thermal remote sensing, that we will measure the radiant temperature emitted by an object, and in most of the cases, since this radiant temperature is related to kinetic temperature, we can use the concept of thermal remote sensing to estimate the temperature of a body which is very far away from us. So this is the main principle behind thermal remote sensing. But this is an ideal case, so we'll see later. So it has been observed that for some other objects, this T kinematic is not exactly equal to the radiant temperature, but radiant temperature is found to be slightly lesser than the kinematic temperature. And this is because of the different emissivity of the object. So we'll come back to this part later. So let's look at this atmospheric window part. Right. So there are different methods of heat transfer. So we have thermonuclear fission reactions within the sun, which generates a lot of heat, and then through so there are 3 processes: conduction, convection, and radiation. Right. So through radiation, this energy reaches the Earth's atmosphere. So this is Earth's atmosphere, and then this is Earth's surface. So here, some of it gets absorbed, some of it gets reflected, some of it gets uh, reflected back to Earth's surface. Then here, it might get reflected or absorbed, and then after a while, it will get emitted. And then from this, whatever the remaining energy which is not trapped by the atmosphere, it will reach the sensor. Right. So here we need the atmospheric windows for this emitted energy to be able to reach the sensors. So we saw that the thermal infrared region is between 3 to 14 micrometers. So here it is shown 3 to 14 micrometers. We have thermal infrared region. So in this region, we see that. So look at this axis. This is 0 to 100. So this it shows transmittance. So the white part it shows how much transmission is allowed, and all the black part it shows absorption. So we see that CO2, H2O, and O3, they are the major causes of absorption in this thermal infrared region. Then there is this window of 5 to 7 micrometers where there is no transmission at all and everything gets absorbed by H2O itself. So this window is not useful for sensing in this region, right? Okay. So for thermal remote sensing, the detectors, they are made in such a way that they are sensitive to these small windows which are available in this 3 to 14 micrometer spectrum. So some of the detectors, they are made to function in this 3 to 5 micrometer range, and others, they are made to function between this 8 to 14 micrometer range, or 7 to 14. And here also between 9.2 to 10.2, we see that there is a strong absorption by O3. So in most of the remote sensing satellites, we see that this band between 10.5 to 12.5 micrometer, this band is used. So here it's shown in this figure. So only this area is used for sensing in the thermal infrared region. Someone has raised a hand.
So, you said something in the range. What happens in the range of 10.5 to 12.5 micrometers?
What happens between?
10.5 to 12.5 micrometers.
Yeah. So when you see this between 10.5 to 12.5, you can see that the maximum transmission window is there. So in this region, most of the thermal infrared radiation which is emitted, this window will not absorb a lot, but there would be more transmission. So it would be better for sensing. So satellites, they are designed in such a way that they are sensitive in this region itself.
So here black portions are absorption and
Yeah,
white
white
portions are.
portions are transmission. Okay, so there are these different windows. So you have this uh, 8 to 9.2 also here, this small window, or here after this absorption band. So you have these small windows. So the satellites, they are designed to be sensitive in these windows because if there is a lot of absorption, then there is no point in making the satellite work in that range. So this is how we can check the atmospheric windows, which would be useful for our thermal remote sensing.
One quick question here. See, basically, when you talk about atmospheric characteristic, right? So wherever in whichever the bandwidth, the absorption is greater. I think in the same band, the transmission also should be greater. Is it the same? What I'm understanding is right or it's wrong?
No, see, if absorption is greater in that band, then the transmission would be very less, right? So if this is Earth's surface and this is these are the atmospheric layers, and these are all the gases and other particles present in the atmosphere. So this is my emitted wavelength. So if it's getting absorbed by this atmospheric layer itself, then very less amount would reach my satellite to be sensed. So if the absorption is higher, then the transmission would be less.
Okay, but see, uh, in general terms, if we think right, so if there is any such radiance, then only there should be like a reflectance, right? So if there is no such radiance, let us suppose in the bandwidth from 0 to 3 to 0 to 4, there is no such absorption. So, but still the reflectance is there, right?
No, what do you mean? I mean, what are you calling radiance exactly?
See, one, let us suppose for the 0 to 0.1 to 0.2, so
Hmm.
the total window is for the absorption
Hmm.
as per the figure, right?
Hmm.
So here what it means is like there's only the activity of absorption is taking place, not the transmission. I mean, like radiating back to the sensor,
Hmm.
right? So
Right.
but see, if there is such absorption, right, when we say absorption, that means some sort of energy is coming from sun, and then and the surface is getting absorbed.
Huh. Okay. Okay. I understood what you're saying. So, uh, absorption. This is so this whole spectrum. It is telling us whether so it is telling us about the absorption characteristics of the atmospheric layer, nothing else. So this is only talking about the atmospheric layer. So if this is showing absorption in the range from point 1 to point 3, then it means that this atmospheric layer is absorbing everything from point 1 to point 3. So even if it's coming from the sun, or if it's going back from the earth's surface, if any radiation is falling in that range, then it would be absorbed by the uh, atmospheric layer itself. So it will, if it's coming from the sun, then it will not be able to reach the earth, or if it's going from the earth, it will not be able to reach the sensor, because everything will be absorbed in the atmosphere itself. So we need to find the windows where this passage is possible from outside to inside and from earth surface to the sensor. So that is why we are finding these small atmospheric windows which allow the passage of this electromagnetic radiation from one side to the other.
Okay.
Okay, so we'll talk about the thermal radiation laws. So first we'll understand what is a black body. So black body is a theoretical construct which absorbs all the radiation that falls on it and emits at highest possible rate per unit area. at, at each wavelength. And then we have Stefan Boltzmann law, which relates the um, spectral radiance excitance, which is MV, to that of the absolute temperature of the body. So we have MV is equal to sigma T to the power 4. So this spectral radiance emitted by the body is directly proportional to the fourth power of the temperature. So we had covered this part before also. The value of this constant is 5.66. 7 into 10 to the power minus 8 watt per meter square. And Wayne's displacement law, it shows the relationship between the temperature of a black body. So this relation is defined for a black body. Right. So Wayne's displacement law, it shows a relation between uh, the wavelength at which we are having the highest emittance and that of the temperature of the body. So the value of this constant is 2898 micrometer Kelvin. Right. So here we need to understand that why do we need to study about this lambda max, right? So uh, lambda max gives us the wavelength at which, so these are the relative radiant energy curves at different temperatures. So this is at 79K, at 195K, 300K, 800K, 3000K, and 6000K. So we see that at different temperatures, this curve is getting bigger and bigger. So the area under this curve would be given to MV, which is the spectral radiance exitance. So this MV would be the area under each of this curve. So as temperature is increasing, the area under this curve is increasing. And what lambda gives us is, it gives us the wavelength. Uh, Anyone have a question? Okay. So what lambda max gives us? It gives us the wavelength at which this curve is at the highest point. So it gives us the maxima of each of the curve. Right. So why do we need to study this lambda max? So if we know the lambda max of a particular body at which is at a particular temperature. So let's say if we are talking about sun. So for sun, the temperature is 6000 Kelvin and its lambda max is around I think 0.5 micron. Okay. So lambda max would tell us the wavelength region around which the maximum energy is being emitted from that object. So if we want to study the if we want to study using the spectrum of the sun, then we would design our sensors in such a way that they are working between this wavelength range. So lambda max would give us an idea about how to use our sensors, like in which wavelength range we should use our sensors so that we can utilize the maximum energy emitted by that object. So for sun, if we are using the uh, if we are using passive remote sensing, then this would be the ideal wavelength region for the instruments to sense in, because in that wavelength region maximum energy from the sun would be in that region. So and also this region, it corresponds with our atmospheric window. So that makes it the best region for studying passive remote sensing. Right. Or we can take another example. So if we want to study the forest fires of temperatures around 800K, so these forest fires would be on the earth's surface, and if they are at the temperature of approximately 800 Kelvin, then their lambda max would be around uh, 3.62 micrometers. So we would design our sensor to work in that wavelength range. So if we look at this atmospheric window, it would be between this 3 to 5, right? So that is why we need to know about lambda max. Or we can take another example, like if we are studying other features on Earth which are similar to that of Earth's temperature, so it would be 300 Kelvin. So for this, the lambda max would be around 9 or something. So for other objects on Earth surface, this window lambda max is around 9. So this 8 to 14 window would be the ideal one to study those features. So depending on the temperature of the objects, we can uh, select the wavelength region um, for us to study in. So this lambda max helps us select the appropriate wavelength region in which the object would be emitting the highest energy. So next we have Planck's radiation law. So this law, it gives us the distribution of spectral intensity as a function of wavelength. So basically, this is the equation of this curve. It's the equation of this curve. Okay, so we'll now see how these three are related: Wien's displacement law, Stefan Boltzmann law, and Planck's radiation law. So this is Planck's radiation law. It gives us how spectral intensity is varying with the wavelength. So it gives us equation of that curve. So, and we saw that Stefan Boltzmann law, it gives us area under the curve. So if we want to derive Stefan Boltzmann law from Planck's radiation law, then we would have to integrate this equation from 0 to infinity. So if we are starting from 0 to infinity, then everything under this curve. So we'll integrate everything under this curve till here. So this would give us the total energy emitted by that body, and the and if we want to find the relation between Planck's radiation law and Wien's displacement law, so Wien's displacement law is giving us lambda max, right? So it's giving us the point. It's giving us the point of maximum. So we need to find the derivative of this equation and then equate it to 0. So the point where this derivative is 0, this point would be our lambda max.
Could you please little bit zoom what is this?
Is it okay?
Yes.
So we'll try to see the derivations of these two equations. So it's not very difficult. So we'll try to derive those. Uh, so this is our equation of Planck's radiation law, and to find m, yeah, mb will be the integration of 0 to infinity 2 pi h c square. So we'll integrate it with respect to d lambda. Here our lambda is variable. So now we will replace d lambda with dx and this term with x in the above equation. So we get so this entire term, this value is equal to pi to the power 4 by 15. So here we will get k to the power 4 upon 15 h cube c square and then t to the power 4. So here we have fourth power of the temperature and all of these they are constant, so it becomes so if we input values of all the constant it will be equal to the Boltzmann constant and then t to the power 4. So here from the Planck's radiation law we can derive the equation for Stephen Boltzmann law. And for Wien's displacement law, what we need to do is d I lambda by d lambda is equal to 0. So at
Could you please
wherever
show
the
previous one?
derivative,
Please show the previous one. Is in MB you have written and within bracket that 1 by uh, that in the denominator that is lambda kb into t or lambda suffix kb. Actually, in the initial expression, it is
oh sorry, yeah, this is not kt. Okay, no, this is not kt. This is lambda into kbt. It's
okay.
Boltzmann constant. It's not the suffix of lambda. Sorry.
Okay, okay, thank you.
Okay, so this is I'll write down this original expression. Uh, Right. So here, when we find the derivative of this expression, everything else is constant. This term has lambda and this has lambda. So we will apply the chain rule. So first function into derivation of second minus second function into derivation of first. So we have 2 pi h c square here. Hmm. So this entire term, so this is the derivative of our intensity. So this entire term is equal to 0. So uh, this part will vanish and then we'll solve this equation. So we have right? So these terms would cancel on both sides. This lambda, we took it to the right hand side. So we divide here by the same term. So we'll rearrange this term to write it as 1 minus e to the power minus hc by lambda kt is equal to 5 times lambda. So when lambda is much smaller than hc by kt, then this whole term it would tend to 0. So we assume here that lambda is smaller than this term, and then we obtain this expression hc by kbt is equal to 5 times lambda. So lambda is equal to hc by 5 times kb and t. So this term, when we input the value, so I have tried this. If you input the values, you will get a, you want, if you go to slightly higher number of decimal places, you will get values close to 2900, so 2890 to 2900 micrometer Kelvin. So you can try doing this hc by 5 kb, and so here this value would be our constant b. So we have lambda is equal to b by t. So this is, so since we are calculating this at the derivative, it would be our lambda max. So this is the derivation. So you can try inputting all the values in this constants and try to see if they match. Okay, so now we have the concept of emissivity. So we know, before we saw Stephen Boltzmann law and Bame's displacement law, everything with respect to a black body. But then in real world, no objects are like black body, right? So they will not emit at highest possible um, uh, rate, but then their rate of emission would be slightly lower than that of the black body. So emissivity, it's the ratio of actual radiance emitted by a body to that of the black body at the same temperature. So epsilon is mr by mb. So this is the spectral radiance of real world object, and this is the black body. Then we have another concept called gray body. So this body emits equally at all the wavelengths, and it consistently has the emissivity value of less than 1. So at epsilon less than 1. And then we have a selective radiator. So selective radiator, it radiates differently in different wavelength range. So look at this plot here on the top. So this line here, on y-axis you have spectral emissivity, and on x-axis you have wavelength. So here, this line, this indicates the black body. So it has the spectral emissivity of 1 at all the wavelengths. So at all wavelengths, it will emit equally. Then we have gray body. So here at 0.1, this is the gray body. So it will have the emissivity of 0.1 equally for all the wavelengths. And then there is selective radiator. So here from in this region it has emissivity of I think approximately zero point 0.3. Then suddenly here the emissivity shoots up, then it becomes 1, then it comes down, then it becomes 0, and then again it increases. So for a selective radiator in different wavelength ranges, they'll have different spectral emissivity, right? So we saw this curve for a black body. Uh, so this is the black body radiation curve, right? So this is the and area under this curve would be MB. So this is the highest possible rate at which a body could emit. So this is for an ideal body for a black body. For a gray body, the shape of the curve will be exactly like the black body, but only it will be displaced to the lower side in along the y-axis. So this is for the gray body. And then for selective radiator, the shape of the curve would change in each wavelength range. So here the shape of this radiator would be like this. Then in this wavelength range, it would almost match to that of the black body because here the emissivity was 1. Then again it will come down. Here it will be almost 0, and then it will rise and come back again. So the spectral radiator will have a different shape throughout. So these are some of the examples of black body radiation curves of the real world objects. So for water, the emissivity is very close to that of a black body. So it's around 0.98. So that is why the curve of water is very close to that of a black body. Then we have granite and dunite, where the emissivity values are 0.86 and 0.78 respectively. So here the curve will show features like a selective radiator. Okay, next we have Kirchhoff's radiation law. So Kirchhoff's radiation law is based on the law of conservation of energy. So when we have this incident radiant flux phi I, and when it's incident on a surface, it will either be reflected or it will be absorbed or it will be transmitted, right? So the total amount of energy which from the law of conservation of energy we know that the total incident energy would be should be equivalent to the total energy leaving the body or getting stored in the body. So we have phi I is equal to phi A plus phi R plus phi T. Now we divide by phi I on both sides. Right, so we have 1 plus alpha lambda plus r lambda plus tau lambda. So this is these are spectral spherical absorbance, reflectance, and transmittance. Right, and it has been observed that the spectral emissivity of the body it is generally equivalent to its spectral absorptance. Right, and for real world objects, most of the objects are opaque, so there would be very less or zero transmission in most of the real world objects. So this Kirchhoff's radiation law is can be updated like this. So we have this transmittance factors become 0. So we have plus r lambda. So instead of alpha, we can write the emissivity parameter. Right. So from the right hand side of left hand side of this equation would be a constant, right? So any changes which are happening in one of these parameters, it would be compensated by the other. So that is why we know that the objects which are good reflectors, they will be very poor emitters. So if an object is reflecting very high, then its r lambda would be high. So all these reflectance values, reflectance or emittance values, they range from 0 to 1. So when an object is a good reflector, then r lambda would be close to, I mean, it would be 0.9 or it would be close to 1, and its emission characteristics would be it would be close to 0. So that is why we say that good reflectors are poor emitters and good absorbers are good emitters. So if we look in the spectral reflectance curve, we know that water is a very good absorbent in the near infrared range and all. So water would be emitting the highest. So there would be, so this emissivity would be higher for the water and it would reflect very less. So if we look at a thermal image, then water would appear brighter in that image because of high emittance. And similarly, we can check for other objects. So like metals and all, they would be reflecting higher, so they would emit less. So this is a nighttime thermal infrared imagery of an airport. So here we see that all these aircrafts, they are appearing darker in this thermal infrared image. And here some of the parts which are appearing brighter, so they are the engines of the aircraft which were on or which have been turned on, so they are emitting more than the rest of the body of the plane. So this explains why these objects, why some objects would appear darker or some objects would appear brighter in the thermal image. Right. So after looking at the emissivity concept, we know that emissivity of real world objects would not be close to that of that of the black body. So if MR, this is my spectral emittance, spectral radiance of my real world object, then I would have to add this emissivity index in front of my black body formula. So depending on this value of emissivity, the energy, the radiance emitted by the real world object would change. So remember before, first we had seen that the concept of kinetic temperature and radiant temperature. So when a body is emitting any kind of radiation, so the radiations emitted by this body, this MB that we saw before, so it would be based on its kinetic temperature. So here we would update this formula as epsilon sigma T kinetic to the power 4. Now for a black body, this because the emissivity of a black body is 1, the temperature which is sensed, which is T rad and T kin, they would be the same because it is emitting at the highest possible rate. So for a black body, this the equation would be can be modified to this sigma T radians to the power 4. Now after we make this change into our real world body uh, energy, we assume that MR is equivalent to MB. So after this correction, we can equate these two equations. So epsilon sigma T kinetic to the power 4 is equal to sigma So, for real world objects whose emissivity is known, the relation between radiant temperature and the kinetic temperature would be given by this. So, if the emissivity of the object is known and radiant temperature is sensed using the remote sensing instruments, then kinetic temperature of the object can be calculated. Or vice versa, if we do not know the emissivity of that object, then we can do in situ measurements and remote sensing measurements to calculate the emissivity of that object. So so epsilon to the power 1 by 4 is equal to T rad by T. So, right. So this radiant temperature is can be calculated using remote sensing, and then kinematic temperature can be calculated using in situ measurements. So this is what we were talking about in the beginning, the relation between the kinematic and radiant temperature. So the concept of emissivity helps us find the relation between radiant and the kinetic temperature. So let's solve one or two problems based on this, and then we'll end this session. So a body with area A and emissivity 0.6 is kept inside a spherical black body. The total heat radiated by the body at temperature T would be given by. So this would be C. So here, when we calculate MB, this is the total energy radiated per unit area. So if we want to calculate the total heat radiated by the body, then we will have to multiply it with the area of the body. We'll try to solve this problem, and then we'll end the session. So we have two bodies, A and B, and here the thermal emissivity is 0.01 and here it's 0.81. The outer surface area of the two bodies are the same, and these two bodies emit total radiant power at the same rate. So M capital A would be equal to M capital B because they're radiating the total radiant power at the same rate. Right. Wavelength lambda b corresponding to the maximum spectral radiance in the radiation from B is shifted from the wavelength corresponding to maximum spectral radiance in the radiance from A by 1 micrometer. So lambda b, it's either on right side or left side of lambda A by 1 micrometer. So if this is the curve for lambda A, lambda B would be either like this or it could be either like this. So temperature of A is also given. So from this relation we have epsilon, area is same only. So we have epsilon sigma T a to the power 4 is equal to epsilon B sigma T b to the power 4. Alright, so TB is 0.33 times TA. So TB turns out to be 934 Kelvin. Right. So, and temperature of A is 5802 Kelvin. So, temperature of A is higher than that of B. So, lambda max of A would be lower than that of B because we saw that from Bain's displacement law, temperature and wavelength they are inversely proportional, and then as the temperature increases, the lambda max keeps on shifting to shorter and shorter wavelengths. So, if TB is less than TA, then lambda max B would be more than lambda max A. So, it would lie on the right hand side on of that of A. Now we need to find lambda max A and lambda max B. So we have the temperature values. So we have this relation TB is equal to 0.33 times TA. So we have TA is approximately 3 times of that of 3B, and we also know that modulus of lambda A minus lambda B is equal to 1 micrometer, and we found that lambda B is greater than lambda A, so we have lambda B minus lambda A is equal to 1 micrometer. So from this relation we have lambda B is equal to 3 times lambda E. So we have 2 times lambda A is equal to 1 micrometer. So lambda A will be 0.5 micrometer and lambda B is 1 micrometer more than that. So lambda B would be equal to 1.5 micrometer. So out of this is true and this is true. Is this question clear? Okay, if there are no doubts, then we will end this session for today, and
And
we'll.
regarding previous question,
Okay. This will be equal to sigma E80 to the power 4.
okay.
Okay, thank you everyone for joining.